Okay, so I presume you're all here for the makeup class. So thank you for coming. What I'm going to do today is to continue the discussion from Monday and wrap up the slides on virtualization. We'll talk about OS virtualization today. Okay, but just for those of you who may not have been familiar with virtualization, I presume a lot of you are, but for those of you who are not, I thought I'll just do a very quick demonstration of both VirtualBox and Docker, so you get some feel for what virtualization can do. Okay, so here I have this application VirtualBox, which runs essentially the type 2 virtualization that I have been discussing. And you will see that I have created one virtual machine here. You can see the parameters of it. It has 2 gig of memory. It has essentially a disk drive, which is a virtual disk. Of course, it has a Ethernet card here, which is again a logical Ethernet card, and so on. Okay, and you can essentially this virtual machine, let it start up. Okay, so now I just started the virtual machine. This is a console, so this is actually a Linux virtual machine. So I basically created a VM, I've installed Linux in it, and this is just the console for Linux. And you'll see if you actually look for it, it'll say it's basically a Linux kernel. It looks for all practical purposes like a Linux machine. Linux is running inside a VM. It does not know it's actually running in a VM as opposed to on a physical machine, because the VM exports an x86 abstraction to it. Okay, you can do whatever you do with normal Linux on this inside this virtual machine. Okay, you can also interestingly just power down the machine, start it up. You can suspend and resume, okay, which you cannot do on a physical machine typically. So I can just stop it, and you can save the state, or you can power it off. So if I just say save, it will just suspend it, and then it's going to save the state. And if I restart it, it will start from that point on. You don't even have to reboot it. So there are many things you can do with a virtual machine that you cannot do with a physical machine as well. Okay, so that's an example of hardware virtualization. I also have an example of Docker. Okay, actually Docker is already running, so I'm going to use a GUI interface just to show you. Okay, so let it start. So here is the GUI interface for Docker. What this is showing is you can actually take many pre-packaged applications and deploy it using a Docker virtual machine. The Docker uses OS level virtualization that I'm going to discuss today. I'm just going to show you an example Docker container that I've installed here. So this is a simple web server, the Nginx web server. And I started it, it's already running. You can actually start a terminal, okay, and you will see that it will. So now I booted into my container again. This looks like a Unix, rather a Linux container. Okay, essentially it's running. It's a Docker container, but it looks like a standard OS. Linux OS inside the container. Now in this case, each container will typically hold one application or a set of processes that belong to one application. You don't have to, but that's how Docker is used. Okay, it will isolate itself from others. So it basically does the same kind of stuff that you see for, and I can then of course stop my Docker container, start it, or install new ones, and so on. Okay, so you will be doing a homework soon where you will be asked to create virtual machines, install Linux, play with Docker, play with Linux containers, and so on, just to get yourself more familiar with this concept. Okay, but that was a very quick overview. Let me ask if there were any questions that you thought of when I was showing you some of these things. Yes? How are these two things different, the containers and... Okay, how are the two things different? So one is using hardware virtualization, VirtualBox, that's what I was talking about last time. Docker uses OS virtualization, which is what I'm going to cover today. They use virtualization at 2 different layers in the stack. One is emulating an entire virtual machine. In the OS case, you basically are creating what is called a lightweight virtual machine. You do not have a full-fledged hypervisor and so on. I'll show what OS virtualization does in a minute. Okay. Any other questions? Yes.
And they use GPU
Okay, question is, can you use GPU in the virtual machine? The virtual machine can use any virtualized hardware resource. So if you virtualize a GPU, yes, you can use a GPU as well. Okay, it depends on what resources you virtualize inside the virtual machine. Okay, yes, question?
Can you virtualize something that doesn't belong to the host?
Question is, can you virtualize something that does not belong to the host? You can certainly use emulators. Emulators can actually emulate devices that may not even be present on that host. Okay, and they have to somehow emulate that device functionality, even though there's no real hardware that you can use to emulate it. So long as you can do that, yes. Okay. Okay. So last time I had talked about how to virtualize the processor. Okay, we talked about how you need the processor to have sensitive instructions that run in kernel mode to throw a trap. So whenever the OS, the guest OS, runs those instructions, you cause a trap, the hypervisor executes them for you. Okay, so we only talked about the processor. I'm going to quickly talk about how memory is virtualized and how the storage resources are virtualized as well. Okay, very briefly. Okay, now as you know, operating systems are responsible for allocating memory to processes that are running on them, and they manage that memory. Okay. Typically, you will use hardware support to manage memory in the form of page tables. Okay. Typically, you will take the process, you will partition it into pages. Pages will be assigned to frames in a RAM, and a page table will keep track of which pages of this process are present where in RAM. Okay. The process is not typically laid out contiguously. You can actually have pages be mapped anywhere in RAM. So you have page tables that will allow you to track this information. Okay. Whenever processes grow in size or shrink in size or new processes arrive, you have to set up page tables or modify page tables. That's the job of the OS. Okay. Now modifying page tables is a privileged or not a privilege, rather it's a sensitive operation. It's only can be done in kernel mode. Processes are not allowed to modify their own page table. Okay. And since in our case the OS actually runs in user mode, not in kernel mode, it's the hypervisor that runs in kernel mode, we have to allow the operating system to modify page tables even though it does not have the privileges to doing so. Okay. And the way this is done is essentially what you will do, or what the hypervisor will do, is it is going to make the page table inside the OS read-only. Okay. So now if the OS tries to modify a read-only page which is in the page table, that's going to generate a trap, because if you try to write to a read-only page in memory, you get an error or a trap. Okay. This is going to cause the trap to go into the hypervisor. So it's the hypervisor that actually manages the page tables for the OS, because the OS cannot do anything. So the hypervisor essentially has the real page table. It will make the modification on behalf of the OS. The OS has a copy of the page table which is referred to as shadow page tables. Okay. So the OS has a page table which is merely a copy of the real page table. It's a shadow of the actual page table which is in the hypervisor. Whenever you try to modify it, you trap into the hypervisor makes the change, and then the shadow page table sees those modifications. Okay. That's how you are going to make the OS believe that it is actually making changes to things like page table, even though it does not have the ability to do so. Okay, is that clear? So that's basically how memory is going to be virtualized. You will allow the OS to make these operations which will trap into the hypervisor. The hypervisor will perform those operations for you. Okay. I/O virtualization is a little more straightforward. In this case, when the guest OS boots up, it will see a disk. Okay, and it will basically try to read or write to that disk. Just as if you normally boot an OS on your machine, it accesses the hard disk on the machine and reads and writes to it. Okay? Except that in this case you are reading and writing to a virtual disk, not the real disk. Okay? And in most cases, virtual disks are just large files that you create on the file system or on the actual disk. Okay? So if you have used VirtualBox or virtual machine, you know there are some things called VMDK files. Okay, so those are essentially large files that pretend to be disks for the purposes of the virtual machine. So you can create a 2 gig file Okay, and then you attach it to the virtual machine, and it sees that file as an actual disk. And then the disk driver is going to read or write to that file, and you are actually writing to a file rather than writing to an underlying disk. Okay, so it's just a raw file, and you just read and write to it exactly the way you would read or write to an actual disk. Okay. So that's basically how you are going to virtualize I/O. You can create a virtual disk of any size and attach it to a virtual machine. Okay, when you create a virtual machine, you have to also specify a disk that you want to create, and it's going to create a blank disk, which is essentially a blank file of that size for you. Okay, so that's disks, and the last resource that you want to typically virtualize is the network interface or the Ethernet card on the machine. Okay. Again, your physical machine, a physical laptop or a PC, is going to have some sort of a network interface. It could be your Wi-Fi card or a wired Ethernet card, doesn't matter. It's a NIC of some sort, and there's an IP address that's assigned to the NIC. Okay. Now, the virtual machine will have its own logical interface. Okay. That's an emulation of an Ethernet card, not the actual Ethernet card. Okay. And that emulated card will pretend like it's a real Ethernet card, but when it needs to send or receive packets, is going to use the features of the underlying physical card to do so. Okay. Just because you emulate a network interface card doesn't mean you can send packets. You have to use a real network interface card to actually send or receive data. So you can have logical NICs that are multiplexed onto the physical NIC. Each logical NIC, for all practical purposes, looks like a real network interface card. You can assign it an IP address that is independent of the underlying physical NIC. Okay? So your VM can have a real IP address, so can your physical machine, and two IP addresses can be different from one another, okay? If you so wish.
But it won't have a MAC address.
Okay. So typically, if you make a logical NIC, you can assign it a MAC address that's different from the physical NIC's MAC address. You can have multiple MAC addresses associated with the physical NIC. Okay. That's possible. These are called virtual MAC addresses. There are many ways to virtualize a NIC. One way is you can give it an independent MAC address. Okay. It just looks like a logical implementation of a network interface card. Okay. Any questions on this? Okay, so just for those of you who are interested in going into more details, I have two handouts that I put up on Moodle, okay, on virtualization. So you should go and read up. Some of what I taught here is not exactly covered in the book, okay, because the book has a very brief introduction to virtualization. Some of the details are not in there, so I made a handout that has some of those details, and I put them up on Moodle, so you can look at that handout. It will give you some of what I was discussing here in a little more detail. Okay, all right. So let me skip this example. We'll come back to it in a little bit. Okay, I'm going to talk next about OS level virtualization. So we just discussed hardware virtualization. The next is OS virtualization. Okay? So just to understand what this is, here are two pictures that show you what OS virtualization does. Okay, so in this case, you boot an operating system, okay, on the machine, and the OS has the capability to create what are called lightweight virtual machines. Okay? They are also called containers. Okay? Essentially, you can run processes or applications inside the container, and they're isolated from anything else that's running on the machine. Anything that runs inside a container, okay, or in an OS virtualized container, cannot see processes that are running outside it. Okay, and the processes outside may not be able to see what's inside. So it's isolated, and inside the container it just looks like a normal virtual machine, except that you're not running an entire OS. Okay, the underlying OS provides all of the OS functionality to the application inside the container. That's what is shown here. Okay? So you will see that there's an OS kernel, and the container runs applications. There is no OS that's running inside the container, unlike hardware virtualization where you actually have an OS. I might have an example here. Okay, so here are the three types of virtualizations we have encountered so far. That's type 1 virtualization. Okay, it's where you run the hypervisor directly on bare metal. Okay, the hypervisor acts as the OS. You have virtual machines. Inside the virtual machines, your guest operating systems and your processes. Okay, that's type 1. Type 2 virtualization is essentially also something we talked about last time. VirtualBox is an example of it. Okay, you run an operating system. okay, which is typically a desktop operating system. Say inside the operating system, or on top of that operating system, rather you run a hypervisor, which is a type 2 hypervisor like VirtualBox or Parallels. And then on that hypervisor, you are going to create a VM. You will then install another OS in there. Okay? In a hardware virtualization, you always have to run an OS inside the machine, because this just looks like a bare bones PC with the emulated PC, and then you have to first boot an OS in it and then run your applications on top. Okay? And this is OS level virtualization, where you have your hardware, you boot an OS in it, and then you create a lightweight virtual machine called a container. Notice that there is no OS running in it. Okay? The underlying OS provides all the OS functionality that the application inside that container needs. Okay? So this is why it's more lightweight, because in these VMs, each of them will need its own operating system that's independent from the others. Here you're going to have one kernel that's shared across all of those containers. So starting and stopping containers, as you can imagine, is much faster, because in hardware virtualization, you have to boot that guest OS first. Here you just start the container and you start the process inside it. Okay, that's what Docker will do as well, as we will see. Okay, so you're virtualizing at a different layer in the stack. You're virtualizing an OS interface instead of virtualizing the hardware itself. Okay, this is why you get a.
So processes are scheduled through the underlying operating system, or Docker is responsible for anything?
Okay, question is, are processes scheduled through the underlying OS, or is Docker responsible? So OS virtual machines have no kernel in them. They cannot do scheduling because there's nothing that so they're relying on the underlying OS. Okay, so the underlying OS will schedule all processes, including those that run inside containers, those that run outside containers.
So you can see the processes which are running inside containers, outside as well.
Okay. So the question is, can you see the processes running inside the container outside? So the kernel knows everything. Okay. So the kernel knows which processes are running, which ones are associated with what containers, which are running normally. Processes may not be able to see one another. The OS can see everything because it's the kernel, it has full privileges. Okay, but one process may not be able to, a process, for example, that's running inside a container cannot see other processes that are running in the machine. The OS is preventing it from doing so. Okay, but the OS can see everything and it can schedule them. Okay, your question there?
Could it be that all the hardware is like distributed and the point of all this is to like give that transparency from this distributed hardware? Is that the
okay, question is the hardware distributed and can you give transparency? This is not distributing the hardware. This is just a single server. Okay? What you are doing is providing what's called isolation. This is not transparency, this is called isolation. So in this example, just to go back to the previous question, you have 3 purple containers which are called zones. In Solaris, containers are called zones, but they just think of them as VM1, VM2, VM3, OS level virtual. And you see that there are 3 applications. When you actually are inside this container and you do something like PS or top, you only see that process, you don't see other processes. When you are inside this container, app2 cannot see application 1 and 3 or the other processes. Okay? The OS will not prevent you from doing it. Okay, and app4 may not be able to see the other application. The OS itself knows all these applications are present and schedules them, but it may prevent them from seeing one another. That gives you isolation. Okay, your question, yes.
So will these resources be competed from one another, for example, memories or?
Okay, question is, will these resources compete for one another? The OS is responsible for allocating memory, CPU resources to processes, whether they're inside or outside containers. Containers, as we will see, also allow you to reserve resources. So you can say this application can get so much CPU and so much memory and so on. In that case, you will respect that allocation. If not, you will dynamically allocate as you do for any process. Okay, yes, question there.
So where exactly is the Docker there? Like, is it integrated in the OS or is it like a user?
Okay, question is, where is Docker? I haven't gotten to Docker yet. We are just talking about basic OS virtualization. I will show you how Docker fits into this. Okay, Docker will use OS virtualization, but it will do something on top. Okay, so yes.
So let's say take BSTJ is the example that you mentioned. So it's like the modification has been done at the OS level to like create the ability to create containers.
Yeah, the question is, has the modification been done at the OS level to create these containers? So any OS that supports OS level virtualization will allow you to create these lightweight VMs. Okay? They are called containers or zones in Solaris. They are called containers in Linux. In BSD, they are called a jail. Jail essentially says you jail a process so it cannot see or access anything outside that jail. Only resources that are allocated to that jail will be accessible to it. Same is true for container. Okay? And these are two examples that essentially show the same thing. That Solaris, that's a more general thing where you have the OS kernel, okay, you have containers and your applications that you're running in them. And whatever is running here, okay, you can log into a container when you will get a shell prompt. Okay? And then if you say PS, you don't see anything that's running outside. That's basically the point because you're providing isolation. Okay?
So what is the benefit
Okay, so what is
the process is outside on the operating system?
Okay, question is what is the benefit? So that's what I'm going to get into. So anytime you need a virtual machine, okay, you can also use a OS level virtual machine. In this case, it's faster than a hardware virtual machine because you don't have to boot the entire OS. Okay, but you can actually isolate the process just as you isolate it on a regular virtual machine. Okay? So if you want scenarios where you want isolation across processes, you basically can create a lightweight virtual machine. Just the same reason why you would create a virtual machine to begin with. You want to take a server resources, you want to partition it into across independent applications that have nothing to do with one another, that don't need to see one another. Of course, you could have run these processes without the container, then they compete with one another. If they are they belong to different users, they might do things that impact the performance of one another and so on. Containers provide isolation. You can allocate certain amount of CPU so that no matter what other processes do, you get your share. You can do this interesting resource allocation, as we will see, that you may not be able to do as easily if you did not isolate them. Okay? So faster provisioning than hardware virtualization. Bare metal performance, because you are actually running, although you are inside a container, you are running on that OS. So there is no slowdown. All other virtualization layer will put a performance penalty. Here there isn't any because you are just running on the OS. This container is not slowing anything down. It's an abstraction that limits your resources. It doesn't actually cause any overhead like you would have in the hypervisor or the guest OS has to have an additional, that's an additional software layer that runs on the OS and so on. Okay, so you get better performance, it is more lightweight and so on. Okay, so let's talk a little bit about how you implement OS virtualization, which will also give you a sense of what are the things it can do. Okay? So there are many things. So in this case, I'm going to talk specifically about Linux containers, which are referred to as Lec06. The concepts are similar across other operating systems as well. So Linux containers have something called namespaces, which is process-based resource isolation. So you can create a container and say these processes belong to it, and other processes can act. So they will they can see one another, but they can not see anything outside that namespace. Okay. You can do C groups, which say now these processes are inside the container, they collectively get 1 gigabyte of RAM and they get 20% of my CPU share. You can make these kinds of allocation and you can say they get 100 megabits of my gigabit Ethernet bandwidth. Okay, and then regardless of what other processes are doing, those processes inside the container are guaranteed those resources. Okay. So you can actually set limits, you can do prioritization and so on. Okay, you can actually also hide some of the files that are present on disk using Linux interfaces like change root. Okay. You can say this container can only see these directories on my disk. They cannot see other directories. Even though those directories are present and outside the container all of those files are visible, inside the container you can limit what part of the disk or what directories are even visible. Okay, so you can do this kind of isolation and allow processes to be limited to what they can see, what they can do on the machine, how much resources they can consume and so on. Okay? And Docker is based on Linux containers. As we'll see, it will add additional tools that allow you to do portability across machines and so on. Okay? Let me go through the namespaces and C groups and then I'll talk a little bit about Docker, which I had showed earlier. Okay? So namespaces, what does that mean? It restricts what processes a container can see. Okay, and you will see this is not very visible here, but you will see that there is a blue namespace, a green namespace, and a red namespace, and that tells you within each namespace you can define what is it that the blue container can see, what is it that the red container, and that's very flexible. You can define it any way you want. Okay, you can say the container can see everything. In that case, you get no isolation at all. Okay, but typically you wouldn't do that. You will restrict what the containers can see. So processes will have the illusion that they're the only process on the machine. Okay, so it looks like you are the only thing running, or this small subset of processes are running, even though there's a lot more running. You can also, as I said, restrict mount points. Even process IDs that are visible can be limited, and so on. Okay, you can also do this at a user level. You can say this container is only accessible by these user accounts on the machine. Okay, so if you have a set of users that have accounts and passwords on that machine, you can say this container can be only accessed by these 3 users. So in that case, if the container is running and a user tries to access the container and you are not part of the authorized list, you can't even access it. Okay, so you can limit access to containers to specific users and so on. Okay, this is a way to limit what the container can see or do. Okay, and then C groups allows you to say what amount of CPU and memory resources are allocated to each of the processes. Okay, so resource isolation is how much can the container use. Okay, this is different from what you can see. Okay, so this is what share of the CPU do you get. So you can set upper bounds on whatever resources you consume, or you can use a technique called fair share, which I'm going to also discuss, that say there is a limitation, but you can fairly share resources in a certain way. I'll talk about fair share as well. Okay, so, and you can do the same thing for I/O. You can say you can use this much amount of disk bandwidth. You can say you can use this amount of storage space and so on. Okay, so let me explain that in a little more detail. Okay, so here's one example that you can use to limit the amount of resources that are allocated. Okay, you can use this technique to either limit CPU resources or network resources, in some cases even disk resources. Okay, and this technique broadly is not limited to containers. They are used in many different contexts, but we'll try to understand them in the context of containers. So it's called proportional share scheduling. Okay, it's a type of scheduler that have been designed, which we did not cover when we were talking about scheduling. Okay, in this case, what happens is you can assign each container a weight, which is an integer. Okay, and the amount of CPU or network that you get is in proportion to your weight. Okay, so in this case, if you have, let's say, 2 containers, okay, and you're given weight, okay, you're given weight of 1:1, okay, then this container gets half the resources, this container gets half the resources. Okay, if you have assigned the first container weight of 1 and the other container weight of 2, okay, this container is going to get 1/3 and this is going to get 2/3. Okay, so you can decide based on the weight what fraction of the CPU you are going to get. Okay, so if you have arbitrary weight W1, W2, W3 up to Wn for n containers, each container is going to essentially get the following fraction, Wi over summation of Wj's. Okay, that's essentially what I did. Okay, you sum up the weights, that's what is appearing in the denominator, so you get 1:3 and 2:3. Here you get 1:2, half and half. Okay, is that clear? Okay, so basically Linux containers have the ability, okay, to assign share. So that says what share of my resource am I going to get, and the share is proportional to the weight. The larger your weight, the larger fraction you are going to get in relation to everyone else's weight. That's the basic idea. And you can control carefully how much resources you get. Okay? And shares are relative. Okay? If you change some other container's weight, your fraction will change. It's not an absolute value. If you get a weight of 1 and some other container at a weight of 1, you share the resources as half and half. But let's say that changes to some other value. You can change the share. So you say, I'm going to now change that other container's weight to 3. Okay, in this case, you are going to get 1/4 and this is going to get 3/4. Okay, so your share will change because you change somebody else's weight. Okay, so it's not an absolute allocation, it's a relative allocation. Okay, so that's share-based allocation. Of course, you can also do absolute allocation by assigning what are called hard limits. In hard limits, you specify an absolute percentage that's allocated to the container. And needless to say, the sum of all the allocations cannot exceed 100%. Okay, so if you say container 1 has 30%, you give it 30%. It doesn't matter whether it uses it or does not use it. Okay, only the remaining 70% is given to everything else. Okay, and you can take that 70 and split it across other containers and so on. So both of these techniques are available in containers. Okay, you can do relative allocations using shares, or you can do absolute allocation using percentage, which will assign hard upper bounds to containers and as well. Okay. Now there are other techniques that are also used or can be used. One of them is called a credit-based allocation. Okay. In a credit-based allocation, you are given, let's say, one token every so many time units. Okay. And you can use resources that are in proportion to the number of tokens you have at any given time. You can spend the tokens that you accumulated. You can never use more than the amount of tokens you have. Okay, so let's say one token gives you 1 millisecond of CPU time. Okay, so if you have 10 tokens, you can get at most 10 milliseconds of CPU time, and if you spend it all, then you have to wait for new tokens to be given, and tokens can be given at some steady rate. That's just the token generation rate. Okay, so these are called credit-based schedulers. So the advantage of a credit-based scheduler is if you're idle for some period of time, you can accumulate tokens. You don't lose that CPU time. You save it and then you can use it later. Right? In a share-based scheduler or in hard limits, if you are given 30%, if you are not using it, you cannot use it at a later time. Okay? Basically, it's just the way cycles are wasted because you just idled. Okay? In a credit-based, you are basically take any share that you are not used at the present time can be used in the future because you are going to use that token at some later time. Okay? So that's the difference between these approaches. In one case, you can actually use any unused capacity later on in the future. So there are a number of different approaches that containers use. I talked about 3 different ways of allocating resources to containers. There are several others as well, which I'm not going to go into. Okay. What should be clear is there are flexible ways to allocate resources to virtual machine. Similar techniques also are present in hardware virtualization. Okay. You can also, in hardware virtualization, say, for if you have virtual box VM, saying this one gets so much resources, the other one gets some other resources, using similar techniques. Okay, so that's something to keep in mind. Okay, so this I'm going to skip. This is just saying that there were all these techniques that were designed. Okay, so just to put all of that together, okay, you have the way you are going to have containers is you will first create a container image. Okay, which is essentially a set of files that belong to that container. When you boot up that container, you're essentially starting the processes that belong to whatever that image has. Okay, you'll start the programs that are in that image, which will start up processes, and the processes will run inside the container. Okay? Depending on what namespaces you have allocated, those processes may be limited from seeing other processes, other files on the system. Okay, so you are going to only see a subset of what is actually present on that system. Okay, namespaces allow you to only view a subset, not the whole everything that's running on the machine or all the files that are present. And again, based on what has been allocated, you can only use a fraction of your resources, not all of the resources on the machine. Okay, that's how you can then create multiple containers and have them all run, but then each one is limited in what it can do, what it can see, how much it can use. Okay, now this figure is a little hard to read, so I'm going to ignore that for a moment. Okay, and then see if there are questions before I talk about Docker. Yes, question.
Can you explain credit-based scheduling again? I don't think I understood.
Okay, question is, what is the credit-based scheduler? Okay. So credit-based scheduler is also a way to allocate some fraction of your CPU, but in a way that allows you to not lose any CPU time that you have not used in the past. Okay. So for example, let's say you have 1 second of CPU time to allocate. Okay. If you say one token gives you 100 milliseconds of CPU time and a container is given 1 token every second, it can at most spend it on 100 milliseconds of CPU time every second. That's so it's now automatically limited how much CPU time you can use. Okay? So depending on the token generation, if you get 2 tokens a second, you can, each token gets you 100 milliseconds, you can use at most 200 milliseconds. So now you got 20% of your CPU bandwidth. Okay, the only difference between, and you could have done the same thing in a share-based scheduler by assigning 2/10 of the weight to that container. That would also have gotten you 20% of the CPU. The main difference in credit-based is if you don't spend a token, you get to keep it. So you can accumulate tokens over time. So if you're idling and you're just accumulating those tokens, you can then use them at a later time, so you can run as a burst and you'll get a lot more CPU time than that 20% you would have normally got. Okay, so if in this second I did not spend my 2 tokens, next second I get 2 more. So now I have 4 tokens in my account. So I can actually run for 400 milliseconds. So over 2 seconds I'm still getting only 400 milliseconds. So I still get 20%, but I can run as a burst, not have to spread it around. Yes.
Could it be that this is like unfair in some cases where say there's an application which is like not doing a good job of using all the resources it got, and then so you're like awarding it for not doing a good job. So like there's some resources which are like just not being used.
Okay. Question is, can credit-based scheduler cause unfairness or rather starvation? Because you can idle for long periods of time, accumulate a set of tokens and then just run, and then if you use up your tokens, it will prevent others from running because you have more tokens, so you will get to use your resources. So that is indeed a problem with credit-based schedulers. Okay. Share-based schedulers are fair in that respect. Okay. They are also, so you will see that there's a fairness property associated. If you got a share, if you didn't use it, that you shouldn't penalize other processes. Here, if you do not run and use your credits, you can run at a later time, which prevents others from running. Okay? That's a disadvantage. But having said that, there are scenarios where this is used. Okay, so on Amazon's cloud, for example, you can get a type of a server called a burstable instance. Burstable instance allow you to run at full speed for a certain number of hours a day, which means you are given those tokens, you can run them or use them all at once, or you can spread them out. The choice is yours. Okay? So if you have application that burst once in a while, you can run faster rather than having to run slowly. So there are some scenarios where it does make sense, which is why it is there at all. Okay? But it can cause unfairness, no question. There's some question here.
So I'd
Yes.
like to ask image of Docker. So I'm not sure if you'll mention later, because when I use Docker, I found that I can actually use different version of Linux on image. So does that mean that I build another OS on top of the original OS?
Okay. Question is, in Docker, you can actually download different images that emulate different versions of the OS. Okay, does that mean you're running multiple kernels? Is that your question? Yes. So as I had mentioned last time, okay, when I talked about virtualization, what virtual machines allow you to do is emulate different interfaces. In OS virtualization, you can emulate the OS interface, which is a system call interface. By default, a container will actually emulate the same interface that is the underlying interface. Okay? Which means the OS version you see inside the container is same as the OS version you use outside the container, which is the native OS interface. Okay? But because there is no reason to have that mapping, inside the container you can emulate some other OS version as well. Okay? So there are containers that will emulate previous versions of the OS. They allow you to run legacy code. The same way mainframe operating systems allowed you to run older code of old operating system version. The same thing can be done in the OS container. It doesn't mean you're running a second kernel. It just means that you're emulating one OS interface using the other OS interface. That's the definition of virtualization. Okay? Other questions here? Okay. All right. So coming back to Docker. So what does Docker do? So there are many Linux containers have been used in many different variants, and you will see that there are actually 4 or 5 different types of Linux containers. So Docker is a very specific technique that takes Linux containers as base mechanism, and it adds portable containers, portability on top. Okay, so what Docker does is it allows you to have portable container deployment. What does that mean? What that essentially says is you can take an application, you can package it as a Docker container, which essentially gives you a set of files. Okay? You can then take those set of files and you can run them on any Docker machine. Okay? So you can just download a Docker image and you can just essentially run it. If so long as your Docker installed, you can run it on one machine. So it makes it much easier to package applications as a Docker image, give it to any user. They just have to download that image and run it, and then it basically runs exactly the way you envisioned it would run. So that's what Docker will add to containers. Now when the Docker image starts up, it will create a fresh container and all of the programs that you are going to start up become processes inside that container. Okay? So this makes it much easier to do software development and deployment. Okay? So if your developer has constructed a new piece of software, they can package it as a Docker image, send it off to someone. They can essentially run it on a server without having to install the OS, or rather install the application, because already installed and configured inside the Docker image. Okay? So it makes software distribution much easier. Okay, the old way of software distribution is you get a, let's say, a tar file, or you get some sort of an image or a CD, you install it, it will install, you configure it, then you start it. Okay, and then there may be many configuration options that you have to pick from. Here you already chosen the right set of deployment features, you constructed it and the image, so you just start the application, there's nothing to really configure and whatnot. So it simplifies the process from deployment, or rather development to deployment. Okay? And it also creates portability for users, so anyone can take a Docker image and run it anywhere. So they are self-contained virtual machines. Okay? Now this feature is not actually limited to Docker. Okay? VMware also has lots of VMware images. VirtualBox also has pre-packaged VirtualBox images. Okay, you don't have to construct a blank VM, install an OS and then run your application. You can actually get a VirtualBox image that has an entire OS and the applications packaged. You just run it and it will boot up. Okay? Except that in that case you have to actually package the OS with the application. Here the OS does not need to be packaged because the OS is outside the container. So they are much smaller in footprint as compared to a full-fledged VirtualBox image or a VMware image. Because you can get rid of the OS, it's not inside the package. Okay, yes, question.
Is it the case that that this way of like deploying software is like maybe in some way inefficient, because they're like, is it like overkill? Maybe if you had like better standards for like all hardware and all software interfaces, maybe you wouldn't have to like isolate everything and give like a Docker image for one application.
Okay, question is this inefficient in some way, because could you have done it differently? And you also asked about isolation. So the isolation does not have anything to do with efficiency. Okay? Isolation simply says I can run multiple applications belonging to arbitrary users and they don't need to see one another, they cannot interfere with it. Isolation just prevents interference. It also guarantees you certain amount of resources that is independent of what other applications are doing. So there's good reason to do isolation regardless. Okay? Now Docker is simply adding portability. There are many ways of doing software development and deployment. Docker is one method that has become popular. Okay? So people can make a Docker image and distribute it, and you can just download it and run it. And that's a very easy way because you can run complex applications without knowing how to install it and so on. So I'm going to go back to that Docker thing that I had started here just to show you. Okay, so here is so if you look here, so these are all pre-packaged Docker images that you can just download and run, and you'll see there are, so you can see Redis, and there is a web server, there is RabbitMQ, there's MongoDB, there's MySQL, there's Memcached, there are games like Minecraft. You basically they are pre-packaged. If you are to actually download one of these pieces of software and install it yourself, you have to read an installation guide saying what should I do, how should I install it, what option should I pick, and so on. Here you don't need to do anything. Okay, you basically just say create, it's going to download that's the size of the image, is going to download that. If you start it, there is some version of it with some default configuration parameters that will start running. So now it's much easier for you to try applications and figure out how things work and so on. Okay? So that's simplification. As now there are some inefficiencies in the sense of whoever created that image picked some choice of configuration parameter, even though that underlying software may have 10 other ways you could have configured it. So if you need to change it, you still need to figure out what to do. But if you're okay with the default, then you get things done much faster. Okay, so this is the picture that you can think about. So you have your container. Docker is just a layer that sits on top that makes it much easier to take applications, package it, distribute it to whoever needs to use your thing. You can use GitHub repositories to keep pushing updates to your containers and so on. So it integrates source code control with deployments and so on. There are some nice features in there that you can do revision histories, and you can roll back or roll forward if there is some problem and so on. So there are many things you can do with Docker that combine software development with software deployment. Okay, so that's basically why it has become popular. Okay, any questions here? Okay, the next homework will actually require you to make a Docker image yourself, okay, and see how all of this works. It will also make you get familiar with VirtualBox, VMs, and so on. Okay, so just so that you have to take what I'm saying here and try it out, otherwise you won't understand some of what I've said in more detail. Okay, so that's coming in a little while when we give out the next homework. Okay, so we talked about Docker already. There are a few other things in Docker that are interesting. Docker uses a special type of file system called a union file system. Okay, so essentially what Docker will do is if you need a set of files and those files already exist on the underlying operating system's file system, you don't have to add them into Docker again. Okay, so Docker will take whatever files are present inside the image and it will construct a union of those files with the underlying file system. So you see a combination of the two. So essentially what that says is you only need to add the diff between what you expect on a normal OS and what the application expects. You don't have to take all of those files and add it. So for example, if you need the C library, okay, if the underlying OS already has a C library, you don't need to put it again inside the Docker image. You can basically say it depends on this library. Okay, so you specify the dependency, and then the file, if you take the underlying files and what's in the Docker, you merge the two and you see the combination of those files. Okay, that's called a union file system. It's a union of what's inside the Docker's image file system and the underlying file system. So that's one thing. The other thing it does is a copy on write file system. Yeah, what that says is copy on write is a standard OS technique, okay, whereby if you have two entities sharing a file, if initially you do not create a copy of that file, but you only create a copy if one of them modifies it, okay, which is called copy on write. Okay, so this is also called lazy copy. Okay, so say you make a copy of a file, typically you expect the primary file and a copy of that file, which are two independent files that take twice the amount of disk space. Okay. If you use copy and write technique, you just pretend like two files exist, but they're pointing to the same underlying data. Okay. When some application takes one of those versions and actually makes a modification, at that point you make a diff. Okay, you basically at that point you may make an actual copy, which is the way to save space. Okay, so you do not increase the amount of storage space you need if you have many copies that are all identical to one another. So you have all of those files point to the same underlying data, because there's no need to make copies if they're pointing to the same underlying object. That's a standard OS technique. There's nothing to do with OS virtualization. Many file systems will use copy on write techniques to make very quick copies without actually taking a lot of storage space and do lazy copy on demand. Okay? So that's called copy on write. The same is true in Docker, where you start with a base Docker image. If you start modifying files inside that image, at that point it will start making copies of the file. Okay? So if you're using files that are actually dependent on the underlying file system, okay, when a process inside the container makes a copy, you make a separate, or writes to a file, you make a separate copy at that time, so that the underlying file is actually not changed. Okay? At that point you have a second copy that is accessible only inside the container but not outside. So you can use sophisticated features like this, which allow you to reduce the amount of disk space that are needed to deploy containers. At the same time, it allows you to flexibly write to files and have your own private copies and make use of disk space as efficiently as possible. Okay? So this allows for very efficient container images. That's basically, these are a whole set of OS tricks that you can use, or file system tricks that you can use to reduce the footprint of a container. Okay, is that clear? All right. So there are many use cases. We talked about this once. So it says essentially once you create the container, you can deploy it anywhere. You can push images to a Git repository and pull it from there and get the latest version by just refreshing your Docker image. It will just pull latest changes, apply them to the Docker image, and suddenly now your new version of your Docker container based on whatever the developer has pushed to you. So you can use source code control to update virtual machines, which is an interesting idea. Okay, and it is essentially very flexible in how you construct it. You can have one process running, you can have a lot of processes running. Depends on how you create your container. Because there's a lot of flexibility in what you decide to put inside and what runs outside. Okay? Any questions here? Okay, the other thing I should say is it is also popular to run what are called microservices. Okay, when we talk about the web services, we will see one popular way of building web applications is to modularize into small services which are called microservices. And microservices communicate with one another to implement a higher level application. Okay? A multi-tier application that we talked about 2 or 3 classes ago is a very coarse-grained partitioning of the application into the HTTP layer, the app server, and the database server. If you then decompose it further into smaller components, eventually you will end up with microservices. Okay, we've been logged out. All right. Okay, so I'm going to wrap up. We only 5 minutes left. So where is virtualization? So we did hardware virtualization and OS level virtualization, and is instructed to understand where all of this is being used today. Okay? Virtualization technology is widely used in many different scenarios. Okay? In data center environments, okay, rather than buying lots of hardware servers, what is more common is to buy a smaller number of large servers, partition your servers into smaller virtual servers using virtualization technology. Each virtual server, for all practical purposes, looks like a normal server. And then you run your application inside virtual servers. Okay, so if you have a small application, say, okay, it needs only 1 core. Okay, you can create a virtual server, assign 1 core to that virtual server, run the application there. And the other cores can be then allocated to other applications. Okay? This is a better approach than running a whole slew of applications on a common OS because they'll interfere with one another. Okay? If some large application starts taking up more CPU time, other applications suffer. So using virtual servers to slice your hardware into smaller logical partitions and running applications in them is one popular approach. Okay? And that's how a lot of these data centers are actually managed. Okay? Cloud computing tech platforms make extensive use of virtualization. Okay? If you go to a cloud provider and say, ask for a server, what you're actually getting is actually a virtual machine, not a physical server. They might say, here's a 2-core server. They're actually giving you a virtual machine that has 2 cores assigned to it. Okay? So they run your code inside a virtual machine. They do not actually give you access to the physical machine. Because if you are going, because what happens is, inside a virtual machine, you run your OS and you have root access. Okay? If you have root access on a machine, okay, the cloud provider has no control over what is happening on that machine. So if you have access to the physical machine, the cloud provider has lost control over that machine. So they retain control by running the hypervisor. So they are the actual root on the machine because they run the hypervisor. They give you a VM and you are root on your VM, but you are not root on the physical machine. So that allows you to rent out your servers to arbitrary customers and let them run whatever they want, yet you have full control because you are the owner of the physical machine and you are root access in the hypervisor. So you can terminate a misbehaving VM, for example, okay, if you want to. Okay. So that's essentially how cloud computing platforms work. Okay, you are going to get root on your virtual server, not on the physical server. Okay, and in desktop computing also this is widely used, mostly for development purposes. Okay, so for example, you might have a Mac, you want to develop a Linux application, you don't need to get a Linux machine to do that. Okay, you can just create a virtual machine, boot Linux in it, and do your code development or testing or whatever you need to do on a VM. Okay, this avoids the need to have lots of machines with different platforms. You can have lots of virtual machines that run different OSs to do testing, development, and so on. Okay, so that's a popular use case. You can do multi-platform software development. You can do testing. You can run apps on another platform. So if you want to run a Windows app and you have a, let's say Mac or Linux, you can make a virtual machine, run Windows in it, and run your application. Okay, so many different scenarios where virtualization is actually helpful. Okay, is that clear? Any questions? Yes.
Would you consider that the case for virtualization for data center applications is reducing because of big data systems like Hadoop, where essentially you can submit jobs, like MapReduce jobs, and you can using a cluster of machines?
Okay, question is the need for virtualization reducing because you have big data application?
Especially for data centers, I understand.
So if you're running these applications in the cloud, okay, your MapReduce cluster is essentially a cluster of virtual machines, not a cluster of physical machines. That's something to keep in mind. Okay, now whether you use virtualization for a distributed cluster is an orthogonal issue. Okay? Even in data centers, you can run your Hadoop cluster with or without virtualization. That is an independent dimension of whether you need virtualization or not. Basically, if you have a large distributed application, you will run that application on lots of machines. Underneath, whether you run it in a virtualized mode or on physical machine is completely an implementation choice. Okay? When you use virtualization, you will see, we have not covered this here, you can get very flexible features. You can move a virtual machine from one physical server to another while it is running. Okay? You can resize the virtual machine. If your application needs more resources, let's say you are running on a 2-core physical server. If you need more resources, you can move it to on a 4-core machine and just expand the size of the VM. You could never do this if you're running on a physical machine. Then you have to literally shut it down, copy your data, restart it. Okay, so there are many examples where virtualization is helpful regardless of the application. Okay? That doesn't say whether it is used for big data applications. In many cases, those don't run in virtual environment. They run on physical clusters other than cloud environments. Okay, so we have any a question?
Is there any shortcomings for OS level virtualization?
Okay, question is, what is the shortcoming for OS level virtualization? That's a good question. There is one important shortcoming of OS level virtualization as compared to hardware virtualization. Okay. In OS level virtualization, all containers share the same kernel. So if you actually do something that triggers a kernel bug, okay, everything on the machine will crash. Okay, because if your OS kernel crashes because of any kernel bug, okay, all other containers will crash as well. Okay. In a hardware virtualization, if an application triggers a bug in the operating system kernel, only that VM crashes. Other VMs are running independent kernels. That has nothing to do with this OS. Okay? So the level of isolation and protection is higher in hardware virtualization than you get in OS virtualization. Okay? That's simply because you're sharing the kernel. Okay? That's a disadvantage. Okay? But there are many advantages as well, as we've seen. Okay, so I want to do one more thing and I'm going to stop. Okay, so this is another case study of where virtualization is used. So this is a system called Planet Lab. Okay, this was designed by researchers for running large distributed experiments. So in this case, you have a set of machines. Each group is deployed in some university, for example. Okay, if you are a networking researcher and you want to do some networking experiment and you need a set of machines, you can essentially go to Planet Lab and say, give me accounts on 10 different locations. Okay? What it does is it essentially creates Linux containers at 10 different locations. It instantiates your user account on those locations and says, okay, done. So then you can just log into those machines and run your code and do whatever experiment you need to do and then go and release your machine. So in some sense, it was an early form of a distributed cloud. Just as in a cloud platform, you can go and say, give me 3 machines, and the provider will boot up 3 machines for you. This was designed specifically to run research experiments by networking researchers. If you want to do measurements between 2 sites using some new protocol and you needed to run your code, this was essentially a way you could do it. Okay? It was all built with OS level virtualization. So you had this notion of a slice, which was essentially a container that got a share of your underlying physical resources. Okay? You could create them very quickly because containers are very easy to instantiate. You can, as I said, associate specific user accounts. So you can only access your container but nothing else on that physical server. You get isolation. Other researchers, other students may be logged into the machine on other containers, may be running their own experiment. Okay, you don't see them, they don't see you. You get to do what you want independent of others. Okay? So all of the isolation, allocation use cases that we saw or discussed is actually used in the context of Planet Lab. Okay? The system still exists. Okay, you can go get a Planet Lab account. Okay, we have some nodes here actually which I manage. And you can run your own experiments. Okay? There are hundreds of sites across the world that are part of this system. Okay? Another example of where virtualization is used, in this case for research, okay, networking research specifically. Okay, so I'm going to stop here. We've run out of time. Okay, so let's continue next time. Okay, it's 5 o'clock.